So hello all. So in this lesson, we are going to discuss about AVL tree construction with one example. So in the previous session, we have discussed about what is AVL tree and what are the properties of AVL tree and the operations of AVL tree, and especially we have discussed the insertion operation for every insertion of a new value. So we have to check whether the tree is balanced or not. If the tree is not balanced, we have to take a rotation. In AVL tree, we have four type of rotation: single rotation, two case, double rotation, two case, totally four cases. So that we have discussed in the previous video. So wait, I will show that also. Yeah. So these are the rotations in the AVL tree. Single rotation, two cases. Left rotation, left subtree of left child. And right rotation, right subtree of right child. If it is LL case, we have to rotate the tree in one step clockwise direction. So one rotation, the node will be moved to one position in clockwise direction. That is LL case. So if it is RR case, right subtree of right child case means if the node will be moved to one position in anti-clockwise direction, that is RR case. The node position will be moved to only one position in the anti-clockwise direction. So these are the two single rotation cases. And the two double rotation cases are right subtree, left subtree of right child case, LR case, right subtree of left child case, that is oral case. So here LR means it is a one first RR rotation followed by LL rotation, two consecutive single rotation. Likewise, for oral case means LL single rotation followed by RR single rotation, two consecutive rotations. That's why it is called as the double rotation. So that we have discussed detailedly how to perform single rotation with example, how to perform the double rotation with example. So now we are going to discuss about the AVL tree construction. So the given input, okay, for the given input, how to create a AVL tree from the starting node to end of the key. So that we are going to discuss with a step by step. Okay. So this and all we have discussed in the previous session. Yeah. So now AVL tree construction with the insertion. Okay. So here there is the values are given in the order 63, 9, 19, 27, 18, 108, 99 and 81. So now we are going to take a first value 63. So here the insertion also same as binary search tree. Where the property of binary search tree is we have to take a value, okay, some root node value lesser than the root node are placed as a left child, greater than the root nodes are placed as a right child. So this is the property of binary search tree. So this property we should maintain in the every subtree also, even left hand side we have to check all the subtree should satisfy the same property of binary search tree. Likewise, in the right hand subtree, right hand side subtree also we have to check whether all the tree will satisfy the binary search tree property. Not only the root node. So for every root we have to check the lesser than the root is left child, greater than the root is right child. So this is the binary search tree concept. So AVL tree is a self-balanced binary search tree. So while constructing this AVL tree, so we have to follow this property strictly. So now let us take a first value 63, and now initial tree is empty. So this is the first node of the tree. It is a root node of the tree. So once the 63 is inserted, we have to check whether the tree is balanced or not. So here only one node in the tree. So that should be a leaf node now. Okay, as per this case now. So this is a leaf node. There is no left and there is no right child. So here the balance factor is height of the left subtree minus height of the right subtree. So here 0. So now it is balanced one. It is a able tree. So it no, it is no violation of able tree property. So if it is no violation means we can proceed for the next insertion. So next we can take a next value 9. So now we have to compare the 9 with the root node 63. If it is lesser than the 63, go to the left child. Okay, left hand side and insert the 9. Okay, so this is the position of 9. So now again after insertion of 9, we have to check the balance factor for all the nodes. So here the balance factor for the 9 is 0 and for the balance factor for the 63 is 1. Okay, so here there is these two are valid balance factor. So here there is no violation. So we can proceed for the next insertion. So next insertion value is 19. So take a 19, compare with the root node. So 19 is lesser than the 63. So go to the left subtree and compare with the 9. So 19 is greater than the 9. So place as a right child of the 9. So now this 19 is inserted. So now check the balance factor for all the three nodes. For the 19, the balance factor is 0. For the 9, the balance factor is minus 1. For the 63, the balance factor is 2. So now these two nodes are contain valid balance factor, but the root node contains not a valid balance factor. So now this is not an AVL tree because it will violate the property of balancing factor. So now we can make a tree as a balanced one. For that, we have to take either the rotation, single rotation or double rotation. But here, this insertion happened after this insertion of 19. Here, the tree structure look like a less than symbol. If it is less than means definitely it is a LR case. Okay, so LR case means less than, oral case means the greater than. So here the structure look like a less than symbol. Okay, wait a minute. So the structure look like a less than symbol. So here we have to take definitely double rotation, not the single rotation. So here, if it is a double rotation means the 19 move to 9 position first, then followed by 63 position. So that's why it is called as a double rotation. Here LR case means RR rotation first followed by the LL rotation. RR rotation means first the 19 move to the 9 position with the anti-clockwise direction. So if it is moved to 19 here and 9 becomes a left child. After that we have to perform the LL case, one step clockwise direction. So 9 becomes a root node. Okay, this sorry, 19 becomes a root node and 9 is a left child and 63 is a right child. So this is the balanced tree. So now we can continue with the next insertion, that is the new value 27. Compare the 27 with the root node 19, it is greater. Compare with the 63, it is lesser. So place as a right left child for the 63. Now check the balance factor. So all are having a valid balance factor. So no violation. So we can proceed for the next insertion. That is next insertion is 18. So compare with the root node 19, it is lesser. Go to the left subtree and it is greater than the 9. Place as a right child of the 9. So now we have to write again the balance factor for all the nodes. If all nodes are having a valid balance factor, so no rules violation. So we can proceed for the next insertion. So the next insertion is 108. So we have to choose a position for 108 where we need to insert the 108. So compare with the root node. If it is lesser, go to the right. It is greater, so go to the right hand side. Again, it is greater. It is placed as a right child of 63. Now check the balance factor for all the nodes. So all are having a valid balance factor. So now the tree is a balanced one. So no issues. We can continue with the further insertion of value 99. For the 99 again compare with the main root 19 greater. Come to the right hand side 63 greater than 99. So it is more to the left and right hand side again. So now compare with the 108, it's 99 is a lesser, so place as a left child for 108. Now, after insertion of 99, again we have to check the balance factor. So all are having a valid balance factor, so no issues. Next, we can move for the next insertion 81. So now, if 81, the location is 99 left hand side. After insertion of this 81, so with the tree is not balanced. So these three nodes have a balance factor of minus 2, and plus 2. So this is not a valid balance factor. So if the tree is an imbalanced one, so to make this tree as a balanced one, we have to call the rotation either single rotation or double rotation case. So now in this case, it's a single rotation case. So here in the single rotation means 99 becomes a root node. Here is a LL case, left subtree case. So 99 become a root node, only one single rotation in the clockwise direction. So 99 becomes a root node and this 81 becomes the left child and this 100 is the right child. So now check the balance factor. So all are having a valid balance factor 0, minus 1, 1. So now this tree is a balanced one. It is an AVL tree. So likewise, we have to construct the value. So every insertion, okay, as per the binary search property, we have to place the value, and after place the value in the tree, we have to check whether the tree is a balanced one or imbalanced one. If it is imbalanced one, we have to take a rotation of single rotation or double rotation. Okay, so then we can get a balanced tree. So this is about AVL tree construction for the given input. So thank you all. We will discuss the next hashing function in next class. So thank you all.